B4. So this is now a particle in a box problem. So this is one that kind of goes a bit further in terms of the understanding and the approach for things. I'm only have 8 minutes left, so I'm going to try to get through as much of this as possible. So first part, right, is simply to just predict the shapes of the bonding wave function at the different energy levels. And so because, right, we're using the particle in a box approach in this case, right, it's the exact same thing, right? So this is the n equals 1 level, right? And so that's just going to be simply this wave, right? N equals 2, right? It looks like this right here, right? N equals 3, you know, you got something that looks like this right here. I'm drawing them, pretty sloppily right now, right? But you then have, that for n equals 4, n equals 5, right, is, what is it, 20%, 40%, 60%, 80%. Right? It would look like that, right? Same thing, right, as we would do with a standard particle in a box problem, right? Is just simply drawing all of those. And so then, part B of the problem asks, on your particle in a box diagram, locate all of the nodes. What is significance of these nodes when it comes to thinking about bonding, right? So one big mistake people run into is they see a node for an atomic orbital or a molecular orbital or anything like that, and they understand that there isn't any electron density there, but they also think that that right there is a point where essentially there's like a bond breakage. But that's not necessarily true, right? It's just simply a region where you don't have any electron density. And as you're going right to higher and higher orbitals, right? I mean, n equals 1, right? You have the electron is delocalized across all 4 of those atoms, right? And when I'm talking about delocalized, right, there's only 2 electrons that are always going to be in that n equals 1 level right there, but they're not just simply confined on one atom or in between 2 atoms, right? They're actually confined across all 4 of them, right? That you can find those 2 electrons at the n equals 1 level across all 4 of those atoms in those cases. And so that's what's happening there, right? These electrons are being distributed across all of them, right? They're not localized in between 2 things. And that's, I think also a hard concept for a lot of people to wrap their heads around when it comes to thinking about bonding, because, we're so used to looking at Lewis structures where, we say like, oh, oxygen and hydrogen, right, in water, right, this oxygen, this hydrogen, right, they're sharing these 2 electrons, and this oxygen, this hydrogen, right, they're sharing 2 electrons. But in reality, right, it's not like that perfect. They're actually getting kind of like, distributed across all of these different regions. And everything. If anybody who watched last week's streams and was looking at any of the stuff that I was doing there, you could kind of see, right, what the different molecular orbitals were looking like, and how electrons were being delocalized and spread out across a lot of different atoms. And that becomes really important when it comes to reactivity and stuff. But in this case right here, right, that's what we're talking about in these instances. Now, the important thing though is that those nodes, if you're putting electrons then into those higher energy orbitals and taking them out of the lower energy ones, now, right, because you're having less electron density in between 2 atoms, that could result in bond breakage if enough electrons are moved around in those cases, right? And that's actually like how a lot of reactions work, where you're starting to put electrons into certain molecular orbitals, and then having electrons in there, right, then results in things breaking apart. We'll talk about bond orders when we get to molecular orbitals, and that'll make more sense. But in terms of thinking about this right here, right, you're really just thinking about that those nodes, right, is going to be the possibility of finding an electron between the 2 of them is equal to 0. And so then in this case right here, right, for part C, I'm not going to go through doing all the math because it's just simply a particle in a box problem, and I was working through that earlier. But all you really have to do is you just simply apply the particle in a box equation, which is E is equal to h squared times n squared over 8ml squared, right? Making sure that the mass is in kilograms and then the length is in nanometers. And so you can calculate what the energies are for the n equals 1 and the n equals 2 levels, right? And then you just simply get the difference there, right? That gives you then the energy difference between the 2 of them. You can take that energy difference and then you can convert that into wavelength, right? Where, what you have is, I guess I could, write all this out, right? So delta E is going to be equal to h squared over 8 ml squared, right? And then it'll just simply be n final squared minus n initial squared, right? And you just plug and chug and stuff like that. And so that gives you that energy for that. And so then all you have to do there, right, is to convert that into wavelength would be hc over lambda in that instance, right? And you just simply solve for lambda, right, which is the wavelength. And you should be able to get these answers in these cases, right? And so then that tells you, right, like how much energy you would need to excite it from one thing into the other. And then, you know, part D, the you know, more of like a question, you know, to think about things, right? It says, you know, if the lithium chain were to continue to grow in length with more and more lithium atoms added to the chain, how would you expect this to affect the energy levels of the different states? And so what you would expect to essentially happen is that, you know, the system would, you know, you're expanding the length further and further, right? And so if you're expanding the length further and further, the energies of the individual levels, right, should become smaller. And if they become smaller, right, then the differences between them should become smaller as well, right? And so they should start to converge together. And that becomes really important. Anybody who's, you know, a materials chemist or a materials scientist, you know, and you start thinking about, you know, something referred to as band gaps. And I think I, you know, had a thing about that previously. I think maybe even in this pack, no, next week's packet, I think I have things about band gaps. But, you know, it's basically, you know, what happens as, you know, along a lot of these chains start to grow and become longer, those band gaps, they start to like, you know, squeeze together. And they just become like a continuum of where the electrons reside. And then, you know, that's how, you know, conductivity and all that stuff happens. So, but yeah, you know, but that's what you would expect to happen, right? Is that because L, right, is in denominator, the higher that number becomes, the smaller the energies become, and then the smaller the energies become, right, the closer they go together. And then for part E, right, all it is just basically taking what you did for part A, looking at that particle in a box, you know, drawing. So I have it right here next to it, and just basically mapping that onto what the actual like calculated molecular orbitals look like, right? So what we can see here is that for this one right here, right, you just simply have a single blob, right, where it's all just simply one phase. And so that matches, you know, the n equals 1 energy level pretty closely, right? You have one right here, right, where you have, you know, and again, right, all you're doing is looking at nodes, right? You have one node right here, right? This has, you know, 4 nodes. This guy has like 3 nodes. And this guy has, or that had 2 nodes, this has 3 nodes, right? And so all you're doing, right, is that this right here, right, is the 2 level. Because again, right, you have a node directly in the middle, right? This right here is the n equals 3 level because you have 2 nodes, right? And they're kind of, you know, around those 2 lithium atoms, the way that you had drawn it right here. Right, you can tell this is the n equals 4 level, right, because it has 3 nodes, right, where you have one node that's in between these 2 lithium atoms, and you have another one that's kind of right in the middle of those 2 lithium atoms. And then you have, you know, n equals 5 is right, this right here, right, where you have then these nodes, and those are all just, you know, kind of sitting right there. So, right, so what we're doing is, you know, taking that, and that's kind of the power. I'm going to do this as like my last thing to talk about, but that's kind of the power I think of, or yeah, I'll do this one, because that I think will probably be a bit tricky for people. But that's kind of the power, right, of a particle in a box, is that it's a very simple equation. It's a very simple process for us to draw out the wave functions and calculate the energy and stuff like that. But you can map it onto real world things, right? So these were computed on the supercomputer cluster we have at Brown, right? Oscar, right? To kind of visualize what's going on. And is it a perfect one-to-one match? No. But is it pretty close for something that I was able to just simply draw? Yes. Right. And that's, you know, for, you know, again, why, you know, however many years ago, probably close to 100 now at this point, right? It's 1921, stuff like that. You know, the last 80 or whatever years, particle in a box, right, was a really great approach to teaching quantum and showing a lot of that stuff, because, you know, you didn't have access to, you know, supercomputers that were running, you know, 216, you know, Xeon cores to calculate, you know, a silly image that looks like this right here. I didn't use that many cores, but right, but like, but that's the you know, the thing that's going on is that you can kind of take the stuff that we have and apply it to these orbitals and get a pretty good approximation, right, of what's going on. And the same thing will be then the case too when we go into molecular orbitals, right? You can still apply a lot of those particle in a box type problems and stuff to those systems and get an idea of what's going on. So, but yeah, so that's this problem. And so the last one I'm going to do